I have to say it's a fairly daunting talk to give, given the expertise in the audience. So please forgive me for any missteps. Um, but to start with, I thought I'd just sort of list out why I think we study the internal kinematics of the MCs. Um, there's multiple reasons. One, just getting some basic parameters of these galaxies, their mass profile, their structure, and their geometry, because this is the starting point for really studying them further. We all use, I think, the MCs as proxies for other galaxies, and so clues to the formation of galaxies generally. Um, they are, especially given the interaction between the LMC and the SMC and the Milky Way, it does give clues to the galaxy evolution and interactions generally, and also the impact on the baryon cycle, how that gets fed into stars and back into the ISM. Um, and one reason I think I personally work on this is that when uh, come up with a basic model to fit the internal kinematics that you observe, that model is never perfect, and it's the imperfections, the things that don't fit your models, that really sometimes are the most interesting things. And so I'll spend some time talking about a few of those things that don't really fit. So in considering internal kinematics, there are multiple components of galaxies that we should consider, and I've just put up a few representative images to show these things. So we have stars, both recently formed and older. We have star clusters, and we have gas, neutral, both atomic and molecular, and also ionized. And and we also have lots of data on all these things. So putting this all together into a picture of the internal kinematics is what we're after. I think if you want to study the internal kinematics of the MCs, there's no better place to start than this paper by Roland in 2002 that really, I think, laid out very nicely the framework and by which you can think about all the possible contributions to the internal kinematics that you observe, including the center of mass motion of both galaxies, results of external forces on those galaxies, which includes precession and nutation and tides, and of course internal rotation, which is often what we're after when looking at the internal kinematics of the MCs, and random versus ordered motions. And so this is just a figure from van der Marel et al. 2002, sort of showing the coordinate system by which this framework is built upon. It's really important to consider the effect in particular of the center of mass motion. Right, so here is just a schematic of an observer looking at a tilted disk, which describes the LMC sort of approximately. It has a center of mass motion vector, which has projections into the line of sight. So we measure line of sight velocities, and we measure tangential motions as proper motions. And so these figures here are showing the contributions both from, and we imagine that this disk is spinning. So this is showing in the line of sight velocity space what the center of mass motion contributions broken up into different components here, and what the internal rotation contribution looks like. And when you combine them all together, so here's the combined center of mass motion signature in line of sight velocities. Combine that with what we think is the internal rotation, signature, you can see that with the position angle of the line of nodes, most of this signature that you see when you observe line of sight velocities on the sky is due to the center of mass motion, right? And the same is true in proper motions. You also have different projections into the tangent plane. And so in order to understand what you observe for internal kinematics, you have to be able to take out the center of mass motion contribution. And so the work on proper motions that Nietzsche and others have done really are important for understanding the internal kinematics of the MCs. And just to demonstrate this, so here is a map of neutral hydrogen gas from Kim et al. 1998. So just taken the flux weighted average velocities from that data cube on the sky. So this is what you would get without accounting for the center of mass motion. And after you take out that center of mass motion contribution, you get this instead. So now the line of nodes, so the maximum gradient in the line of sight velocity has shifted from being mostly up down in this figure to at this angle. And you can see that how you would interpret this as a rotating galaxy is quite different. So I can't stress this enough that this is really important to do. We'll come back to this picture again in a bit as well. So what are the different observational measurements that we make for stars? We, for a long time, were only able to measure line of sight velocities and proper motions coarsely from ground-based data. But now with the HST work and Gaia, of course, we have line of sight velocities and proper motions for many stars. For the gas, we have line of sight velocities for different components of the gas, including both from emission and absorption. And I'll mention that briefly, and you hear more about that later today too, I think. So very briefly, when modeling all of these effects together, right? So you can make multi-parameter fits of to the internal kinematics that you observe, including the center of mass and the center of mass coordinates, center of mass velocity vector, disk inclination and angle of the line of nodes, the rotation curve shape and the amplitude, velocity dispersion components. In the case of the SMC, you also need to consider tidal expansion, as we'll see. And depending on the group that has and the data set that has been used, this might be done using either 1D or 2D or 3D velocities, depending on what data are available. This is just an example of a multi-parameter fit to 3D velocity data that I have done myself, just showing that you do get nice fits to the data. There are some correlations between parameters, particularly in the rotation curve parameters. But many of these papers, I think, rely on MC fitting, in particular Dan Foreman-Mackey's MC package. So I think he's done a real service in giving this to the community. I put up a few, some of the references for groups that have done fitting. It's there are a lot of papers to read on this topic, and I'm sure I haven't captured all of them, but there's a ton of interest and data and analysis that have gone into this, so you can't really do it all justice. Wanted to show the SMC first. This is from Paul Zivic's paper in 2021 showing the results of a multi-parameter fit to the internal kinematics, taking all these components into account. And so this is showing at larger scale and then a zoom in into the interior. So in the SMC in particular, he found signs of weak rotation in the inner parts. In the outer parts, that rotation really disappears and it's dominated by tides. You can see the rotation velocity, which is quite uncertain here, is only 20 kilometers a second. We all know that the SMC is quite disturbed, and you might hear more about that as well. And want to point out this paper by Claire Murray that has a very interesting take on the SMC. And the LMC here is analysis done with HST proper motions and ground-based line of sight velocities, so three-dimensional velocities from Menormal and Kalivalilo, showing the rotation curves that you get from different populations of stars. That for the young stars, you see the rise in the rotation curve and flattening at around 90 kilometers a second, implying a circular velocity of this when accounting for the effect of velocity dispersion and asymmetric drift. In the old stars, of course, it's a shallower rise and lower amplitude because more of the motion has gone into random disordered motions, and asymmetric drift means that you see that suppressed. But this is all consistent with a mass of something like 10 to the 10th solar masses within 9 kiloparsecs or so, and a virial mass that when you extend out to the likely size of the dark matter halo of something like 10 to the 11th. There is a paper by Jimenez Arranz that shows that population distribution more finely and resolves the asymmetric drift in time quite well. Also consistent, I think, with within 8 kiloparsecs of the rotation curve amplitude of something like 90 kilometers a second. So similar mass profile. They did see signs of the effect of the bar and the spiral arm in the kinematics. So you can look at the VR radial velocity or radius in the plane component versus V phi, showing that VR changes as a function of radius, and that's mostly seen in the inner parts where the bar and the spiral arm affect the kinematics. Wanted to point out, so if you go out, right, you're limited by the number of stars that you can get in the LMC disk, but we think, of course, the dark matter goes out much further. Laura Watkins recently published a paper looking at the 3D velocities of globular clusters, which go out to 13 kiloparsecs or so, showing that the velocity continues to remain flat out to those radii, and so implying something like an enclosed mass of 2.6 times 10 to the 10th solar masses within that 13 kiloparsecs, again consistent with the virial mass of 1 or 2 times 10 to the 11th solar masses. So a massive LMC, and I think Gertina may talk about this more. So I wanted to get to the topic of looking at departures from the simple kinematic models. Here is a paper that we published on the red supergiant kinematics and also kinematics of older stars, showing that very similar fit to what you just saw from the previous figures. Basically an amplitude of something like 90 kilometers a second in the red supergiants. And these are plotted on top of the H1 velocity. So what we've done here is basically deproject the velocity. So assuming that all of the line of sight velocity variation, once you've taken out the center of mass motion contribution, is due to rotation in the disk, what would that in-plane circular velocity look like? And so you see that the H1 has a flat rotation curve that follows those red supergiants very nicely. It also has all this other stuff. These things here, for instance, we'll look at, but they connect our signatures of the tidal arms of the LMC. You do get a consistent rotation curve here when you look at just the proper motions. This is from Helmy et al. So getting back to that figure I showed earlier of the map of the H1, right? So if you identify or point out the tidal arms that were identified by Stavely Smith et al. From that Kim et al. 1998 data, and you plot that on top of this diagram of circular velocity versus radius, those arms map to these features in this diagram. And so you can see that these sort of departures from that rising and flattened rotation curve really show you where those tidal arms are. You can do the reverse by just drawing out the flat rotation curve here, identifying these things, pieces of gas that don't follow that, and you get this map of the LMC. This bow tie is a region where I've excluded the data because the deprojection factors become very big. But you can see the tidal arm features here and the main rotating disk of the LMC gas. So to put this in context of the H1 emission, this from David's paper with this beautiful figure of the Magellanic Stream and the Magellanic Clouds, these tidal arms, they connect to the leading arm and to the bridge and to the Magellanic Stream here. So we'll look at that a little bit further. In this paper in 2011, we looked at also the kinematics of the older stars, and you can see that many of the older stars in our sample, they follow this flat rotation curve defined by the red supergiants with a slightly reduced amplitude due to asymmetric drift. But there's a number of stars that you could pick out that lie on top of this kinematic feature that defines the H1 tidal arms. And just to highlight this, we took a residual around our model, looked at basically the wings of the residuals and highlighted those in blue and red here, and those pick out those stars that really lie on top of this area. Have to be a little careful, right? Because as we've realized later, that because this rotation curve model has a knee here, and the way that we parameterized it, there's a tendency, I think, to pick out when you select outliers from the residual distribution, you can see maybe the impact of this knee in the rotation curve. So we're have to be a little careful about that. But if you take those outliers, so here is the full sample of old red stars that we looked at that shows the rotation signature, basically a gradient from red to blue here. And you look at the outliers, they have an apparent line of sight signature that is the opposite gradient, basically going from red to blue. And this is about 5% of the total sample. If you didn't have proper motion data, which of course we do now, you have two interpretations, and you could assume that they're rotating in the disk of the LMC, but actually counter rotating, or that they're rotating in the same sense as the LMC disk, but with a different geometry. So basically, a tilted plane with respect to the LMC disk. So with proper motions, you can see that these outliers, which are the blue arrows, compared to the red arrows, which are the normal disk population, they rotate in the same sense. And I've taken the model subtracted it from the vectors, and then averaged in order to beat down the noise, you can see that the red points, which are the normal stars, basically disappeared to 0. The blue arrows are the averaged proper motions from the outliers. So there's a little bit of a signature left in the outlier population, but it doesn't really stand out. It does seem, these are outliers in the line of sight velocity space, but not so much in the proper motions. We also looked at, since we now can get abundances for some of the stars from apogee, here is the LMC abundance distribution. Here is the SMC abundance distribution. These outliers are in the orange. So they're sort of in between, right? I mean, they're, okay. You have, on average, more metal poor stars than you would in the LMC. And so our conclusion was that given the association with the tidal arms and the low metallicities, that these might be stripped SMC stars in the LMC disk. Wanted to briefly show this figure from the paper by Yong Zheng et al. She'll talk about that later, I think, so I won't say very much. But showing that if you look in the ionized gas kinematics, that there she has a picture for how you can get observed outflows in the LMC that includes basically protecting the LMC disk and its gas through a bow shock as it moves through the Milky Way halo, and measuring with absorption line observations whether there are outflows or inflows into the disk. And sulfur 2, you can see that there are these 2 points over here where we see the signature of in the H1 of that tidal arm, and where we think there might be gas flowing in, that there might be inflows there. So this is a sort of some evidence for inflow that I think needs to be further followed up. I wanted to say that if you this paper by Oxendorf also take the view that along these tidal arms that there is inflow of gas, particularly arm E, and this is what is producing the very heavy star formation activity in 30 Doradus. And if you look at the young stellar objects and the massive young stellar objects, you can see that those are highly concentrated, of course, towards 30 Dor. So it might be that this interaction and the gas flows and the capture of SMC stars is all tied together to be forming really active star formation in the LMC disk. This sort of situation arises naturally if you had a collision between the LMC and the SMC, as in the model by Gertina, which she will talk about. Yumi Choi has looked at using our kinematic models and applying that same kinematic analysis to the simulation data to see whether the residuals that you see from the proper motion field are can be made consistent with various stages in the simulations from Gertina, and it shows that the sort of the most recent collision, if it occurred, is it 250 or so million years ago, is too recent to really match the data. If you look at the level of noise or sort of disorder in the residual proper motion field, that it really needs a bit of time to quiet down, but it does appear to be consistent with this model where you have a collision that disturbed the LMC disk. using these internal kinematic models to look for outliers is also useful for studying the periphery. And here's a paper by Xinlong Cheng et al., where we've taken our kinematic model and to pick out outliers in the periphery that you really see quite well in the southern periphery. And Xinlong studies the potential origin using the 3D velocities and metallicities of these stars to conclude that it looks to be a mix of LMC and SMC debris. So these kinematic models are useful for finding that. I want to point out that there are many other papers that are also looking at the periphery and the kinematics. So I'll just conclude that, and we have a lot of data now on internal kinematics in the clouds, including from Gaia, and that we can really explore the internal kinematics in really good detail. I think the models, they point to strong interactions as being important for understanding that kinematics. And my own view is that there's so much data now and models and work on this that taking all the data and constructing a consistent picture of the Magellanic Clouds, I think, is challenging, but also gives you the opportunity to find those things that don't fit, which are usually pretty interesting. So thanks.
That was great. Thank you. So we have a few minutes for Q&A. I just want to remind everybody that I'm going to bring the mic to you so that folks online can hear as well. So any questions? I should speak in the mic too.
Hey, Knut, thanks for this awesome talk. A little bit of a philosophical question. What is your fantasy data that you want but don't have yet?
My fantasy data set, I think, would include parallaxes of every star, so we get distances, right? And along with the 3D velocity vectors. So it'd be great if we could launch a probe to the other side of the galaxy and take those measurements.
Thanks, that was really interesting. I was thinking back to our discussion yesterday about, timing, mutual orbits and star formation and so forth. And from this work that you showed, Yumi's work, do you think there are any prospects that we can actually measure any timescales for star formation, young stars from disturbed gas? I just feel like we're at the brink of being able to actually throw in some timing numbers, but I don't know if that's just a fantasy.
Yeah, I think so. So Yumi, in her paper, she did come up with a timing estimate based on how long it would take for the given, assuming that this is a reasonable model to describe it, and there's debate over the exact model, of course, and so it's model dependent. But how long it takes for the kinematics to quiet down. But I guess so you're asking about using like stellar ages to time this. Yeah, I think if we can, think about
maybe a discussion.
Yeah, yes, that's right.
Because there's so many.
Yeah. It's a good question.
Any more questions? I saw one hand.
Hi, Knut. Thanks for your wonderful summary. Just a comment. So you showed some plots of rotation curves for different populations that show asymmetric drift, which at some level is a very well-known and kind of classical disk heating effect. What has puzzled me personally a lot over the last 20 years is that people study the Magellanic Clouds and the LMC in particular with tons of different tracers, and everyone fits viewing angles, distances, whatever. People never get the same answer to within their random errors, right?
Yeah.
So there's really a lot of evidence that different populations do much more than just having asymmetric drift.
Mhm.
You know, they don't have the same viewing angles. They may be inclined with respect to each other. You know, the Cepheids may be displaced from the rest of the disk. So
Yeah.
there's a lot of things going on as a function of age that would be really interesting to understand better.
Yeah.
And that probably much of that probably points to non-equilibrium dynamics.
Yeah.
But that's something that would be really nice to tie down, is to actually study all the populations and get the same answer,
Yeah.
rather than everyone writing about RLI or Cepheids or red supergiants or carbon stars, and everyone just always gets different answers. Especially viewing angles, it's totally embarrassing. There's this like 20-degree giant thing in the sky that is the closest galaxy to us, and we can't determine to better than 5 or 10 degrees how we're looking at it.
Right.
With a gazillion stars to average over. It's really ridiculous.
Yeah. It's a great point. And I've struggled a lot, and I think people get different answers on this, to come up with a consistent dynamical center, depending on the populations. That wanders all over the place. And if you can get one for the stars that looks reasonable, then you compare it to the H1, and suddenly the H1 rotation curve looks bifurcated and crazy. So yeah, there are a lot of disturbances that clearly are there, and I think the way to pick them out, as you've suggested, I think, is to try to combine all the data in this self-consistent physical picture, which is probably a pretty complicated thing to do, but will be interesting. Yeah.
Thank you so much. All right, let's give Knut another round. Tina, can you hear us?
Yes. Can you hear me?
Hear you great. Okay. So next up is Gertina Besla, who will be talking about a theoretical framework for understanding the internal dynamics of the MCs.
Awesome. Thanks, everyone. I'd like to thank the organizers for allowing me to give this talk remotely. Many apologies for not being there in person. So today I'm going to be presenting a theoretical framework that is derived from hydrodynamic and n-body simulations of the clouds. And this is needed in order to study galactic dynamics, star formation triggers, ISM physics, and just in general using these kinematic data sets that are coming out for the stars and the ISM in the clouds. We have amazing data sets from Gaia, so that data is shown here in the left and middle panels there, but we've also got incredible data sets for the ISM, and especially, we have SDSS-5 coming out. So the work I'm going to present is, in concert with a number of my collaborators, and they really center around this basic premise of a framework. So the idea is that the present day internal gaseous and stellar kinematics of the LMC and SMC are primarily governed by two key physical processes. The first one being that there is a recent, roughly within the past 150 million years, direct, less than 5 kpc impact parameter collision between the LMC and the SMC, all right? And the second point is that there are hydrodynamic interactions at work, both with the Milky Way's CGM, but also, very importantly, with each other. So I'm going to spend the bulk of my talk discussing some of the consequences or evidence for this collision and also for these hydrodynamic interactions, and try to convince you of this story. So the models I'm utilizing are ones that I created back in 2012 now. It's been a while. And they rely on, the idea that the LMC and the SMC are a binary system, right? So they're bound to one another. They've come in more recently into our Milky Way environment within the past giga-year or so. Before that time, they spent as a binary interacting with each other. And this is a movie showing you the gas evolution of this binary, where the SMC is orbiting around the LMC. And as they do this, there are interactions that cause bridges and tails to form. So this is, classic Toomey 1972 theory. And so every time you get close, you'll get a bridge that is forming here, for example, and a tail. Okay. So in these models, to get this kind of an orbit, to get these sorts of interactions, the LMC and SMC are about an order of magnitude more massive than earlier studies have assumed. So this is, building off of all the details you got from Knut. The LMC's halo in particular is a 1.8 by 10 to the 11 solar mass structure, modeled as a Hernquist sphere. These models have live gas and stellar disks, live halos, and then they're going to be, it's a 1 to 10 encounter, and they'll be dropped into the Milky Way, which is modeled in these simulations in particular, modeled as a static halo, and that has been done by other authors more recently with a live system. So this idea is that these galaxies have already been interacting with each other, and so they've already got gas being removed from the system, and then they come into the virial radius and they fall in towards the Milky Way. And these structures that have already been forming continue to form. There's additional interactions, and then they're stretched out, right, to form the stream, the leading arm, and structures, and the bridge. Okay, so in this paper, I presented 2 different scenarios for how you get basically the same story. And I call them Model 1 and Model 2. And the main takeaway point here, the difference between these 2 models, is the interaction history between the LMC and the SMC. So in Model 1, there are 3 encounters between the SMC and the LMC. So what's plotted here is the SMC's position with respect to the LMC as a function of time, today being, all the way to the right. So they're interacting as a binary for somewhere between 5 to 6 billion years before they fall into the Milky Way's environment. And the Milky Way infall point is indicated by these stars. So in Model 1, the SMC has maybe 3 encounters with the LMC, and in Model 2, it has 4. The other important point is that after they fall into the Milky Way's environment, the Milky Way's tides start to become more important, and they will distort the orbital history of the SMC and the LMC. So it's different than if it were left alone in the outskirts of the Milky Way. So this is indicated by the red line versus the black line. So in Model 1, the important point is that the SMC never gets much closer to the LMC than about 20 kiloparsecs. And in Model 2, they have an actual direct collision, which is, with an impact parameter, less than 2 kpc. And in this particular model, it's about 100 million years ago. Okay, so that's the idea. Model 1, no collision. Model 2, there is a collision. So stronger interactions between the LMC and the SMC, but otherwise the premise is the same. Okay, so in both cases, you allow the whole system to fall in towards the Milky Way. And when you do this, you get the same basic structures. You get a stream, you get a leading arm, you get a bridge. And so that occurs for both models. And, nothing, these are difficult simulations. Everything is not perfect, right? But the basics framework here is there. So you get, this is in gas, and you'll get a counterpart to all these structures in stars. And so there's going to be stars in the stream as well, and I'll leave that to Vedant to talk about later. But otherwise, you get more or less the same answer on the large scale for both of these galaxies. The difference is in the detailed internal kinematics and internal structure of the LMC and the SMC. So both of these models give you the large scale things, what you want, but the difference is there's a collision, and as a result, the internal structures of both of these galaxies are different. So let's talk about this in more detail. So we'll start with the LMC stellar disk. Now, a collision may seem like a dramatic thing to do to these galaxies, right? How can they survive through all of this? Well, we remember that we adopted an LMC halo model, that is around 2 by 10 to the 11 solar masses. So it's not a tiny galaxy, it's quite robust. And after a collision, the disk of the galaxy is fine. The LMC survives this collision. And these are what you're looking at here are line of sight velocity fields to stellar particles. These are representing the old stellar population in the LMC. So I should point out that there is star formation in these simulations. So there is a young population as well that you can look at. So on the left is Model 1, on the right is Model 2, and you get a reasonable line of sight velocity field, and in both galaxies, even though in Model 2, the SMC has plowed directly through it. But let's again look at it in detail. So what I've done is I put a slit along the major kinematic axis of these galaxies. So just look at the red rectangle, and then the minor axis would be perpendicular to that. And then we're going to look at the velocity along this slit. So this is this red line here in model 1, and the red line is the thing to look at in model 2. The slit in this image has been centered on the photometric center of the LMC in the simulation, and that would be the center of the bar. And so in model 1, that center, the photometric center and the kinematic center are aligned. They're the same place. And as Knut, we just heard about in the discussion, we know that the LMC center, kinematic center, is a mess. And depending on what stellar population or depending on the stars you're looking at or the gas, you're going to get different answers. And in particular, the kinematic center of the gas is not aligned with the photometric center. And that happens in model 2. So this is the photometric center, again, at 0, right, going along the slit. But the kinematic center is offset from that. So you can make that happen if you have a collision. So this is the first evidence that something is going on, that the LMC is not in a state of equilibrium. So Knut also mentioned this work by Yumi Choi, looking at the internal proper motion field using red clump stars in the Gaia datasets. And you get the data from Gaia, you fit a model to it, you take out the model, you get residuals, and then you can look at the distribution of these residuals. You compare this to the models. And so this is model 1 and model 2. And as Knut mentioned, in model 1, so, okay, this is the probability distribution of their proper motion residuals. The red is the observations. And then in blue here, this is the residuals you get from model 1. Remember, model 1 has no collision, and you get a very different answer for the residuals. It's too well behaved, right? In model 2, you kind of get a bit of the extreme. You have this tail out here. So it's actually that the idea is that this collision that happened 100 million years ago in the simulation is too recent. The LMC disk is still too highly perturbed relative to the data. And then, as Knut mentioned, Yumi did some extrapolations from additional, basically we took the same model 2 and we continued it forward in time, and we looked at how long did it take the disk to settle down. And it took another 50 to 60 million years relative to the original model 2 simulation. And so we concluded that you can get, if you have a collision, 2 to 5 kpc impact parameter between the clouds, it'll take about 140 or 160 million years for the disk to settle down so that you get a reasonable set of residuals relative to the data. This is super exciting. I mean, we're really in an era where we can use the data from Gaia with these internal proper motions and really constrain the models in such a detailed way. So this is super, super cool. So that's the disk, the stellar disk, but let's talk more about the gas disk. And in order to understand what's going on there, the really interesting story is the bar. So the bar of the LMC is weird. It doesn't show up in the ISM at all. It's booming in the R band. And then if you try to look for it in the gas distribution or in star formation or in dust, it's just not there. And in particular, the kinematics of the gas don't show it there. And that is really, really weird. And in particular, it's very difficult to get rid of a bar in the gas distribution in a simulation. The bar loves just to funnel gas along it, and you'll see it booming in the gas density. And this is an example. This is model 1. Again, no collision. And what you're looking at here is the present day stellar disk of the LMC on the left. And then in the middle, you have the gas distribution, and then you can see the bar very clearly in the gas. And then this is the gas in a line of sight frame, the velocity field. So it's, a well-defined gas disk, and their bar is right there. And that is just not consistent with what the LMC looks like. But if you have a collision, something funny happens. There's the bar, and I've shown it with a yellow circle just so it's obvious where it is. You look at the gas density, and it's gone. And then if you look in the velocity field, this is a slightly different viewing perspective. It's just line of sight versus deprojected. So the bar is not actually aligned with the minor axis. So in the other, here you can see the contours, the bar is here, and it's aligned with the minor axis of the kinematics in the gas disk. And that is not true anymore after a collision. So what happened? So if you, this is a movie showing, it's following the LMC as it falls into the Milky Way in an edge-on viewing perspective. And then the SMC is going to smash right through it. And when that happens, the inner region tilts. So work by Yumi and others have shown that the bar in the LMC is off-centered and it's tilted up to 5 to 15 degrees relative to the rest of the LMC's disk. So this occurs when the SMC collides through the LMC. But exactly why this happens, and this isn't obvious. There's a dynamic process that's going on here that we're working on figuring out. So stay tuned. There's going to be updating upcoming work by graduate student Himanshu Rathore, along with Kate Daniel. But the key here is that a collision can help you understand why the bar doesn't behave like what you would expect a bar to in normal galaxies. All right, moving forwards, the LMC's gas disk and the CGM. So this is an image that's showing you the, and there's an optical image of the LMC and SMC, and then overlaid our H1 density contours. And the H1 is severely truncated relative to the stellar extent of the LMC. This image of the LMC is not nearly as deep as you can go. This is an image that's significantly deeper from Mackey et al., showing that the stellar density, the stellar disk of the LMC extends out significantly further than this image shows. So the gas disk is severely truncated relative to the stellar extent, and it's truncated in the direction of motion. And so what our team did, led by Munir Salem, was to use wind tunnel style simulations, hydrodynamic simulations using the code ENSO, and simulate the ram pressure effects on the LMC's gas disk as it falls into the Milky Way for the first time. So what you're looking at here is the gas velocity field from these simulations. There are 3 simulations shown with different levels of ram pressure, and the data is shown on the bottom right. So you can have some pretty extreme examples, which is the top right here, where the gas disk is very truncated, and then our preferred model is the bottom left. But the important point that I wanted to raise here is that even if you truncate the gas disk significantly, the internal gas kinematics is actually largely unaffected by ram pressure. So you can't appeal to the Milky Way CGM to explain the peculiarities inside the LMC's gas disk itself. Its kinematics are being driven by other processes, largely collision, ongoing star formation, stellar feedback. As well, we've realized recently, this is work that's been led by David Seton, who's now a postdoc Princeton fellow over at Princeton, that the LMC is moving at roughly Mach 2, and that means that a bow shock must form. And so we've made predictions for where this bow shock should be. It has a standoff radius of something like 6.7 kiloparsecs. It's 60 kpc in diameter. It's this huge thing on the sky. And I'm going to leave this to Chris Carr and also to Yang to talk in more detail about the implications of that. But the idea here is that the kinematics of the disk may be protected at present day because of this bow shock. All right, the SMC. Okay, so what is this thing, right? This is the question that we had yesterday, with this amazing drawing of exactly everyone's feelings in this picture, right? So, okay, so what's going on? So from the data, and we're going to hear more from Claire about this, right? There's a gas velocity gradient that we know exists across the face of the SMC. So there's some sort of kinematic something going on. Is this a rotation curve? It's definitely a gradient, right? Okay, so we know that there's something there in the kinematics for the gas. Knut just showed this, which is that when you look at the stellar body, particularly the old stars, there's really no rotation, right? And the outer part here with these the residual proper motion vectors here look like it's being stripped apart. It's going in one direction here, it's going in another direction there, and then the inside it's just not rotating. And the lack of stellar rotation that has been observed has caused several theoretical studies to model the SMC initially as an old stellar spheroid with a gas disk. So that scenario is not physical, and I'm going to talk about this in a little bit more, right? But this is the reason is because you have a gas, velocity field, and then you have no rotation in the stars. Okay, so the SMC is a gas-rich galaxy. It has as much gas as it has stars. Gas-rich galaxies have gas disks That's seen in the Little Things survey, and they also have stellar disks. And if you take the baryonic Tully-Fisher relationship, and this is a plot from Roland and Nithya's paper, right? The LMC falls nicely on it. And if you take the baryon fraction or the baryon mass of the SMC, you're going to get an expectation that it should have a rotation curve of about 60 kilometers per second. And if you have a gas disk moving at something like 60 kilometers per second or so, you're going to also have a stellar disk that has the same kinematic signature. So why you have to start with a gas and stellar disk and yet somehow end up without one, a rotation, I mean. So I'm not going to get into too much of the details of what's going on, but I do want to explain some of the outcomes of model 2 after the SMC has collided through the LMC. So when you look at it like down the barrel or in a line of sight view, the SMC looks pretty modest in size. It's something like 2 to 4 kpc in extent in the simulations. This is the gas density. But if you look at it from edge on, it looks very different. It's very extended along the line of sight, right? So we're looking this way. I'm turning the simulations around a little bit to make the case more obvious. But you're looking through a huge amount of material. And the main body is in the center, and then there's this at the bottom. And this is what's been referred to in the literature as the counter bridge or a tidal tail, right? This is the tidal tail counterpart to the bridge. And this has been shown by a lot of authors. It shows up in pretty much every simulation, is what you would expect, because this is from Toomey 1972. You should have a tidal structure on the that is opposite to the bridge. And what is interesting is that the kinematics of that, this is all super preliminary, so please don't put this out anywhere. But this structure is moving in a different direction than the main body. So if you look down the barrel of this, you're going to get multiple populations with, there'll be young stars forming all over the place here, but you'll have different populations moving at in different directions. So you can get multi-component velocity structures without relying on, a more exotic solution like the LMCs or the SMCs is 2 different galaxies, right? Which is not a dynamically stable configuration. Okay, so this is, I think, the crux of what is going on here. If Gaia has, again, more incredible data where you look at the young stars and you look in this wing structure of the SMC, and it looks like these stars are just being pulled out of the SMC, moving towards the LMC. And we've compared these types of data sets using HST, led by Paul Zivik and Nithya, and we've looked and shown that this kind of signature is consistent with a collision scenario in a hydrodynamic simulation. And so what's going on here now, this is the same movie that I showed before of the LMC's disk, but now you're looking at the gas. And so this is the moment the SMC slams right through and continues, and it pulls out a high gas density structure. And this is what explains the high gas density of the bridge relative to the stream, because the bridge is being formed recently through a direct collision. You actually have ram pressure occurring because of the SMC as a gas structure moving through the gas disk of the LMC. And with the high densities, you can get star formation occurring here, which you can't get in the stream. So the answer to what is the SMC is that the SMC is a low mass irregular galaxy that is in transition to becoming a low mass elliptical. So through interactions, particularly through a direct collision, its entire internal structure is being changed. So I'm advocating for a direct collision between these 2 galaxies so we can think a little bit more about how probable or how needed this is. And so I'm pointing here to some work by Lara, and then I think Camila is also going to talk more about this, so I'm not going to get into the details here. But you can explain a lot of the structure or the kinematics of the outskirts of the LMC's disk without relying on a direct collision. In particular, you need is some interactions with an SMC where the SMC crosses the disk plane of the LMC. Right, so what I'm showing here is a plot of, this is the last encounter between the LMC and SMC, the timing relative to the separation at that timing. So what is the impact parameter of that interaction? And what's color-coded here is the relative velocity today, but each point represents a different possible relative solution to the SMC's orbit around the LMC from the proper motion error space. And I've computed this using an analytic model for the LMC and SMC. So this is not derived from n-body simulations. And this tells you the available solution set for an interaction between the LMC and the SMC from the proper motions. And model 1 would be up here. Model 2 would be all the way down there. And the star is the mean result. Now, Lara made a really nice point in her paper where, we say that there's a close encounter, right? So all of these solutions are within 20 kiloparsecs, but a close encounter doesn't actually mean a collision. It can simply mean a disk crossing. And here's an illustration. This is from an upcoming paper that hopefully Nithya and I will one day finish. And so this is in the LMC's disk frame. So the LMC's disk is here. All of these individual points here are actual potential solutions for the center of mass of the SMC, which is really not well constrained. This is a large part of the problem here. Even a kiloparsec or 2 makes a big difference because it turns out that the SMC is almost exactly in line with the disk of the SMC is almost directly in line with the disk of the LMC. So if you have solutions where the SMC is a little bit above the disk plane, you get these collisions, right? The orbit will go through the disk. If you have them below, you get solutions where you have disk crossings all the way out here. And yeah, you can get a 7, the actual mean result, the star here is in this red orbit. And this red orbit doesn't actually smash through the disk, right? So the mean result wouldn't actually have a collision, it would be a disk crossing. However, these solutions that I'm showing here are based on analytic models. These are not live halos, and these 2 galaxies are massive and they're close together. So this is wrong. You can't do that this way. It's a great first start, but this is not going to be the final answer. But regardless, the angular momentum vector, so the sense of the orbit of the SMC around the LMC is pretty well constrained. You can't actually change that. And I just want to make sure that that is clear, right? And this is the direction that all the works, apart from a few, have taken. All right, so a collision, the idea that the LMC and SMC are colliding through one and have collided recently actually requires them to be a long-lived binary. And if you have a long-lived binary, you're going to need a very massive LMC in order to make that happen, particularly in the face of Milky Way tides. Now, the alternative to them not being a binary is that they randomly collided while in orbit around the Milky Way. And I really like this paper by Hongsheng Zhao, which actually showed us a solution for the orbit of the LMC and the SMC in the about the Milky Way in MOND. And in this scenario, the LMC SMC are not a binary. And the green orbit here is the LMC. This is kind of X, and this is the disk plane of the Milky Way versus the z-axis and galactocentric coordinates. And so the center would be that 0 here in the middle, and the black dotted line is the SMC's orbit, and the green one is the LMC. And don't worry about the rest of them. So the LMC would make these kind of loops around the Milky Way, or maybe even it comes in for the first time. But in a case where they're not a binary, the SMC then has to be going around and around the Milky Way for basically a Hubble time. And if that's true, why does the SMC still have gas? Right. So this scenario, if you don't have them as a binary, the alternative is the SMC is going around the Milky Way, the LMC comes in and hits it. So, there's some probability of that, but it's low. The last thing I wanted to say is that there are broader implications for this scenario for LMC and SMC analogs. There are systems that look like the LMC and SMC out there in the local volume. This is one example, NGC 4485, 4490. It's surrounded by a 50 kpc H1 structure shown here in the contours. And Sarah Pearson has done the heroic job of taking a stab at modeling this system, and it requires an orbit that's actually an awful lot like the LMC and the SMC. And you'll get a collision between these galaxies, and that helps to understand its current structure. So if you want to understand LMC analogs and SMC analogs in the field broadly, and this can also help us understand how low mass galaxies transition from from irregular type into gas poor elliptical types. I think these interactions are an important key part of the problem or solution. So conclusions: the clouds are not in equilibrium or steady state, right? This is the basic crux of the whole problem. So if you want to look at your kinematic data, you need to look at it with that lens. the internal stellar and gas kinematics of the clouds can't be explained by Milky Way tides alone. So all the simulations I showed you, even Model 1, is subject to Milky Way tides and wide encounters between the clouds, but you can't explain the detailed internal structure and kinematics without a collision. And so, you know, all these things get explained, and you also need hydrodynamic interactions in order to form the bridge properly, truncate the gas disk, form a bow shock. And so, yeah, the framework requires a binary, a massive LMC, and a first infall to the Milky Way. And yeah, and you could broadly explain other analogs through this framework as well. Thanks.
Excellent. Thank you so much, Bertina. I think we have time for one question. A couple hands up. We have 2 questions.
I can do a quick one.
I think a quick one is where we are.
Hi, Tina. This is Andy Fox. Thank you for the great review. So just about the bow shock, right? So you pointed out the LMC is moving at Mach 2 compared to the Milky Way. But if there's a halo of gas around the LMC, right, and there's some evidence for that that we're going to hear about tomorrow, that could change that, right? So like we're not going to have a naked LMC coming in with no halo. If it has its own halo, that would impact the interaction. I just wondered if you could comment on that.
Yeah. Hey, Andy. Yeah, totally. I'm going to punt that question over to Chris, because Chris is going to show you exactly what happens in that scenario, and it's super cool and wild. So, but great question. So yeah, he'll talk about it in his talk.
Okay, so it's Maria Rosa here. Thank you for the great talk. 2 quick questions. One is, since we are getting better and better in getting ages for some stars, and like, you know, if you take the Cepheids populations, you can distinguish some of those that are younger than 100 million years or about that age, and those that are 200 million years old, which would be right, you know, if your collision is at 150, do you think we have a chance of being able to trace the debris before, you know, for older and younger stars?
Yeah, so this goes to Roland's comment at the end of Knut's talk when you were thinking about timing for different stellar populations. I absolutely think we can do stuff. We can constrain the models and understand, potentially really start to constrain star formation through these kinds of timing. A collision actually opens a huge door and opportunity. I do think that the young stellar populations around that timeline will be telling us something about this collision, because it's going to, stars that are forming out of the gas that's been disturbed, right, will have a different kinematic signature relative to an older stellar population. So I think there's a lot of opportunity space here to do this. We need better star formation models for these simulations. This is going to take a lot of work, but I think there's a really huge opportunity space to really get into the weeds of the microphysics. I think one of the biggest pressing problems at the moment in simulation space is, how do you connect global star formation to local star formation? How do we actually get down star forming regions? And the LMC and SMC are a wonderful place to try and test this type of problem, because it's potentially tractable. The galaxies are small enough that you know, we might be able to do something here, and feedback is incredibly important for the structure of the LMC. I mean, there's huge holes in it. 30 Doradus is this huge star forming region. So I really do think that there's something we can do there, Maria Rosa, and I'm excited to use all the data that y'all are coming out with to look at this in more detail.
Wonderful. Okay, let's thank our speaker again. Thank you.